Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session, the chapter D and F block elements from inorganic chemistry. So after the general properties of transition elements, we are going to see about some important compounds of transition elements. The compounds are potassium permanganate and potassium dichromate. So before enter into the study of compounds, let us find what are oxides and oxoanions of transition elements. The oxides and oxoanions of transition elements, they are simply formed. How oxides are formed first of all? The transition metal, when it is heated with molecular oxygen at a very high temperature, they used to form metallic oxide. But the metallic oxide, we know very well, the oxides are either acidic oxide, basic oxide, neutral oxide or amphoteric oxides. So in such cases, when we go down the group of D block element, metallic character increases. When metallic character increases, then their ionic formation of the oxides will also be increased. So when we compare the four different transition series of D block element, except 3D series, the other series 4D, 5D and 6D series used to form more ionic oxides. And we know well, and these transition elements used to form the variable oxidation state, and the oxidation number that varies from +2 to +8 as far as considering the entire D block element. Or if we consider only the 3D series, where the highest oxidation number is +7 and the lowest possible oxidation number is +2. So depends on the different oxidation states of the metallic oxides. Those are classified as acidic oxides, basic oxides, amphoteric oxides and neutral oxides. Okay, so in this case, when the oxides with the highest oxidation number, they are used to be in acidic oxides. So those oxides are able to dissolve in water and forming their corresponding acids. For example, Mn2O7, it is in its +7 oxidation state, and chromic oxide, it is in its the highest oxidation state of +6, and both of them are being acidic oxides. They dissolve in water to form their corresponding acids. So the formation of acid HMnO4 is said to be manganic acid. This is dichromic acid, and H2CrO4 is chromic acid. In dichromate as well as in chromate, both of them, the chromium, it is in +6 state only, and in the manganic acid, manganese is in its +7 oxidation state. So these are oxides. When these oxides dissolve in water, they are forming their corresponding acids, and those anionic parts of the acids are said to be oxoanions. Now let us classify what kind of oxides may be acidic or basic or amphoteric. So the oxides with the lower oxidation number, they might be either amphoteric oxides or even basic oxides. Acidic oxide, we said the element should always be in its higher oxidation state. But in the amphoteric oxides or the basic oxides, the metals which will be in their lower oxidation state. Probably the variation of basic nature to acidic nature, that goes from lower oxidation to higher oxidation state. So in between of the lower and higher oxidation state are mostly in amphoteric nature. So let us discuss about the taking an example of oxides of manganese. Manganese is able to form MnO, Mn2O3, Mn3O4, MnO2 and Mn2O7. So here their oxidation number changes from +2 to +3, and here it is actually 8/3, but oxidation number never be fraction, but by considering their structure only oxidation number we have to calculate. But as far as in their level of understanding the concept, we are taking the oxidation number of manganese is in its 8/3 state, and in MnO2 it is +4 and Mn2O7 it is +7. So here the metals which are in lower oxidation state of oxides found to be basic, and the metals in its higher oxidation state is found to be in acidic. So the intermediate oxidation states of +3 or 8/3 or +4 are being in amphoteric oxide. Acidic, we know they have acidic property. Upon dissolving in water they used to form acids. And basic oxide, when it can react with acids to form salt and water. So acidic oxide reacts with the bases to form salt and water, and basic oxides they can react with acids to form salt and water. What about amphoteric oxides? These amphoteric oxides, they possess both acidic behavior as well as basic behavior, since they do react both with acids as well as bases to form salts. But acidic oxides, they used to form salts only with bases. For example, I can say this HMnO4 can react with the potassium hydroxide to form potassium permanganate. Similarly, the basic oxide MnO, it is basic in nature. When it reacts with the acid, say MnO plus HCl, able to form MnCl2 and H2O. But in the case of amphoteric oxides, they do react both with the bases as well as with acids. That's why those oxides are said to be amphoteric oxides. That's all the oxides and oxoanions of transition metals. The first compound of transition metal is potassium dichromate. Potassium dichromate formula K2Cr2O7. Potassium dichromate. Cr2O7 2- ion is usually said to be dichromate ion. So in this dichromate ion, the chromium, it is in +6 oxidation state. So the oxidation state of chromium in the salt is +6. As it has the higher oxidation number, it is used as the strongest oxidizing agents. Preparation of potassium dichromate. Actually, potassium dichromate is prepared from chromite ore. Chromite ore is the oxides of iron and chromium. It is a double oxide and that can be represented as FeO.Cr2O3, or you can add all the element FeCrO4. This can also be written for the chromite ore. But for our convenience, we are making this compound as FeO and Cr2O3 to identify their oxidation state and to balance the chemical reaction. Okay. The first step is conversion of chromite ore into sodium chromate. So that can be formed by treating chromite ore. First of all, the chromite ore is finely divided into the powdered state, followed by treating with a mild alkaline solution of sodium carbonate in presence of excess of oxygen. So where chromite ore is converted into sodium chromate, ferric oxide and carbon dioxide. This carbon dioxide from carbonate ore and the ferrous oxide is oxidized to ferric oxide, and the chromate is simply converted into sodium chromate. So in this case, we have to balance the equation, because for the completely balanced equation can only score the marks. If we write simply the statements, or if we write an unbalanced chemical equation, that would not be awarded. So we have to balance. The balancing is very simple if we know about the change in oxidation state of the elements where it occur actually in reactant side and the product side. So before how to balance the reaction, let us find whether the number of atoms on both sides are almost same or different. So here chromium I have 2 in chromite ore, and hence I am just multiplying the sodium chromate as 2. At the same time, iron is present 2 times in the ferric oxide, but in this chromite ore iron present as 1 time. So first of all, let me count and balance, then we can go with the oxidation number for balancing the rest of the cases. Okay, so 2FeOCr2O3. Now the chromium it becomes 2 2s are 4. That's why sodium chromate is multiplied by 4 times. Now let us find the oxidation states of the element. Carbonate, sodium, dichromate, there is no change in their oxidation state. This is +1, this is +4, this is -2, and here -2, chromium +6. Everywhere the oxidation state of these elements did not vary. Even in this it is +4, carbon it is in +4, this is 2 into -2, that goes -4. So where actually the reaction takes place? Actually, ferrous oxide is oxidized to ferric oxide and oxygen is reduced to carbon dioxide. This is what actual reaction takes place when chromite ore treated with sodium carbonate and oxygen. So here we found out where oxidation and reduction taken place. So FeO +2 to +3. Actually there is a loss of 1 electron. Here the oxidation number increases. If you find the increase in oxidation number, that is said to be oxidation reaction. How many number of electron? Number of unit increases +2 to +3. So only 1 unit increases. So we can say ferrous oxide is changed into ferric oxide by the loss of 1 electron. So I have given loss of 1 electron. So this reaction is oxidation reaction. But in ferric oxide I have 2 iron atom, but in ferrous oxide I have 1. That's why I made it as 2. Now I can multiply the 2 ferrous atom, that gives 2 electron. That's why it forms ferric oxide. Now these electrons must be received by the another element, then only the redox reaction will be completed. Here the loss of electron is being gained by the molecular oxygen, where it is converted into -2. That means 1 oxygen atom that gain 2 electron. That's why it is decreased 0 to -2. Oxidation number decreases. So when oxidation number decreases, that reaction is said to be reduction reaction. So here I can find there are 2 oxygen atom in a molecule of oxygen. Therefore, for 1 oxygen, if at all it gains 2 electron, I have to multiply by the number of oxygen atoms. So oxygen requires 4 electron, but iron can give only 2 electron. So during the redox reaction, the number of electrons transferred must be same. If at all it needs 4 electron, those 4 electron to be given by iron. So as to consider, we are going to balance it. So now once again this number is balanced by 2. So when it is multiplied by 2, here 2 into 2, this becomes 4 times. So 4FeO, and here 4Fu, you can write it as a 2Fe2. The next one, 4 2s are 8 Cr. So this it's multiplied by 8 Na2CrO4. And here sodium becomes 8 Na2. So sodium carbonate is also multiplied by 8. And carbonate group is 8 times, and hence carbon dioxide is also 8 times. What about now the number of oxygen atom? All other elements are balanced. We yet to balance only the number of oxygen atom. You may find 4 3s are 12, 4 1 is 4, 12 plus 4 here 16 oxygen, and here 8 3s are 24, 24 plus 16, that is equal to 40 oxygen. Here 8 4s are 32, 2 3s are 6, 38, 8 2s are 16, so 38 plus 16, that is equal to 54 oxygen. So product side I have 54 oxygen atoms, but reactant side 24 plus 16 equal to 40 oxygen atom. So there is a difference of 14 oxygen. So this oxygen is multiplied by 7 times. So the equation gets balanced. So when we know about where the reaction actually taken place, that means where it is oxidized, which of the element is reduced, if we know that two sides, then the balancing of equation will be very simple. Okay, the first step we completed, chromite ore is converted into sodium chromate. The second step, we are going to convert sodium chromate into sodium dichromate, Na2Cr2O7. So that can be done simply by treating with sulfuric acid. So when it is treated with the sulfuric acid, we have to take a calculated amount of sulfuric acid only, where sodium chromate is just converted into sodium dichromate. This is a reason chromium it is in +6 state, dichromate also chromium it is in +6 state. The chromate and dichromate molecules are ions are interconvertible. In acid medium you will get dichromate ion. Suppose if it is present in basic medium, we will get chromate ion. Now I want to convert chromate into dichromate, that's why I am treating disodium chromate with acid. In acid medium only I can have dichromate. This is the reason we are treating with sulfuric acid. And Na2Cr4 simply treated with the sulfuric acid, it forms Na2Cr2O7, sodium sulfate and water. By balancing the reaction, very simple, here no redox reaction, it is not at all redox reaction. So we can count the atom, Na2, Cr 2 times present, that's why 2 Na2Cr4. 2 Na2, Na2Cr2O7, Na2SO4. So now we have SO4 and hydrogen, you can make it as 2H2SO4, because SO4 we have one time. So Na2SO4 we have H2SO4. Now oxygen atom, hydrogen, 2 4s are 8 oxygen, 7 over here. So the rest of 1 oxygen with the hydrogen, that makes water. So equation gets balanced. Now how this sodium sulfate is being removed, because we need to have only sodium dichromate. That can be done by boiling the mixture at a hot condition and cooling down, where the crystals of sodium sulfate will be separated as Na2SO4 2H2O. So the resulting solution can be filtered off. The filtrate contains sodium dichromate and the precipitate is simply the crystals of sodium sulfate dihydrate. Okay. We are going to prepare potassium dichromate, but we achieved the preparation of sodium dichromate. Now we have to convert sodium dichromate into potassium dichromate. That can be done simply by treating with the potassium chloride aqueous solution. We will get potassium dichromate and sodium chloride. Okay, why don't we have sodium dichromate? Why it is necessary to convert into potassium dichromate? This is the reason why, because sodium dichromate is readily soluble in water, but at the same time potassium dichromate less readily soluble in water. So we can have the crystals of potassium dichromate can have a longer lifetime, or potassium, if at all we have a sodium dichromate, that can even absorb the moisture that becomes a solution. So to protect the formation of salt only, we are converting sodium dichromate into potassium dichromate. That's all the different steps involved in the preparation of potassium dichromate. You have to remember the stepwise process. It is not necessary to write all the content of the chemical reactions and all. You are going to write the steps along with the equations. It is far enough to have the complete mark for a question. Okay. So you have to remember, chromite ore is the mineral for the preparation of potassium dichromate. First stage, dichromate into chromate, first step chromite ore into sodium chromate. Second step, sodium chromate into dichromate. Third step, sodium dichromate into potassium dichromate. Last step is the conversion of sodium dichromate into potassium dichromate. So we have given all of the reactions as molecular form. The second step of the reaction can also be given in its ionic form. Ionic form is nothing. We are treating the sodium chromate with acid. Acid is represented by proton, that is H plus ion. So you can write the equation E1 like this. Na2CrO4 plus H plus, that gives Na2Cr2O7 along with water and Na plus ion. Why Na plus ion? Because I have 2 chromium, so this is multiplied by 2 times. 2 Na2 I have, so I can write there are 2 Na plus, and water 2 4s are 8 oxygen, 7 plus 1 8 oxygen, 2 hydrogen, so it is multiplied by 2 times. So we can write even the molecular reaction, or even it can be written in the ionic form of equations also. Nothing make a difference. Okay. That's all the preparation of potassium dichromate. Upon the crystallization of sodium dichromate, we will get orange crystals of potassium dichromate compound. Followed by the preparation of potassium dichromate, let us find the properties of dichromate. So actually the aqueous solution of dichromate and chromate are interconvertible. In acid medium, this dichromate will be predominant, as if at all it is in the basic medium, the chromate becomes predominant. So how it is dichromate, chromate ion, when it is treated with the H plus, we get dichromate and water. Or if dichromate is treated with the base, that is the basic alkaline medium, it forms chromate and water. So H plus, that makes the acidic medium where pH of the solution goes less than 7. At the same time, the OH minus, that makes that basic medium, here the pH of the solution, it goes greater than 7. So we can say chromate and dichromate are interconvertible, depends on the pH of the medium. If in acidic medium dichromate is predominantly present, or if it is in basic medium chromate is predominantly present. You can balance the reaction, very simple, Cr2, so it is multiplied by 2 Cr, 8 oxygen, 7, here 8 hydrogen 2 times, so it is multiplied by 2. And in the case of dichromate, chromium 2 times, so chromate is multiplied by 2, and OH minus is there, we have to take 2 hydrogen, and hence this is also 2 times. When we balance the ionic equation, we have to balance both the charges also. We balanced the number of atoms, at the same time we have to balance the charges too. So here 2 2s are minus 4, 2 plus, minus 4 plus 2, the net value is minus 2. Here 2 minus, it is equal to 4 minus, 2 2s are 4 minus. So the charges also be balanced in this reaction. Let us find the structure of chromate and dichromate ion. In this, the chromium is the central atom, to which the oxygen atom is tetrahedrally bonded with central chromium. So here valency of oxygen is 2, and hence with the central chromium the oxygen that can have double bond, and the 2 more negative charges that can lie over the oxygen atom, so that makes single bond with the central chromium. Similarly, in the dichromate ion, there are 2 tetrahedral unit, they are linked by oxygen atom. So in this case, this oxygen behaves as a bridging oxygen atom. So here this is one tetrahedral unit, this is another tetrahedral unit. When we compare their bond length and bond angle, chromium oxygen chromium bond is found to be, bond angle is found to be 126 degree, and the chromium middle central oxygen atom bond length is longer, as well as the chromium oxygen bond length in one of the tetrahedral unit is 163 picometer. If the same bond angle if at all observed in chromate ion, the chromium oxygen bond length is 166 picometer because of the single unit of chromate, here dichromate. That's why the bond length is a little bit varied. Chemical properties of potassium dichromate. The color of potassium dichromate is orange crystal, and we can have that chromate also, that color is yellow colored crystal. So just we have to remember color of the crystals. Dichromate is in orange colored crystal and chromate it is in yellow colored crystals. Okay, now let us find the chemical properties of potassium dichromate. Potassium dichromate in this Cr2O7 2- ion. Here the oxidation number of chromium is +6. How to calculate oxidation number of a particular element in a compound? Let us find oxidation number of chromate ion. Here I have Cr2O7 2-. So if at all a neutral compound where the sum of oxidation number is always equal to 0. But in this case dichromate ion, it is an anionic species carrying the charge. So I have to equate the sum of these oxidation number equal to the charge carried by the ion. So we can find, this is what I am going to calculate for the chromium only, oxidation number to be found out. So I can have, this is an unknown element 2 times present, so it is taken as 2x. And oxygen I have 7 times. Each oxygen they have the -2 state. So 7 oxygen, 7 into -2 and the charge equal to -2. So we are writing the sum of oxidation number of each ions, that is equal to the charge carried by the ion. You can simplify. 2x is equal to 12 or x equal to 12 by 2, that is equal to +6. When we write the oxidation number, the sign plus and minus must be given. Valency only have no charges, but oxidation number they bear either a positive or negative charge. So this is the way how to calculate oxidation number of any element in a given compound or even in its radical. Action of heat on potassium dichromate. Potassium dichromate, when it is heated, it gives potassium chromate, chromic oxide and oxygen. This equation we have to balance. Before that we have to find out their oxidation number of these elements. Oxygen it takes -0 and in this case oxygen it is in -2. Chromium it is +6, just now we calculated for dichromate, and in this chromate also they have a same oxidation number. Chromate, dichromate, both of them are interconvertible because they have same oxidation number. So in chromate also chromium has +6, but in chromic oxide it is equal to +3. How? 3 2s are -6. This is 2x. 2x minus 6 equal to 0 or x equal to 6 by 2, that is equal to 3. Now let us find this +6 to +3 oxidation number decreases. So here gain of 3 electron. Here -2 to 0, so oxidation number increases, their loss of 2 electron. So one oxygen that can lose 2 electron. How many oxygen I have? 2. So I can multiply this is by 2 equal to 4 electron. And here one chromium that changes from +6 to +3, but I have 2 chromium in +6, but it requires 6 electron. That's why this is multiplied by 2, 6 electron. So we have to find a common factor for the number of electron. Why? These two numbers are totally different, but transfer of electron should always be same. So how can we find the common factor? Just I will tell, this is chromium, this is oxygen, it requires 6, it can give only 4. So take the common factor, divide by 2, you will get a 3 and 2. So now this 2 will be multiplied by chromium, this 3 will be multiplied with the oxygen. So this oxygen is multiplied by 2. 3. So this is totally 3. Therefore 3 4s are 12 electron. And here I said 2 into chromium. So this chromic oxide is multiplied by 2. Now this entire is multiplied by 2. 2 6 are 12 electron. So transfer of electron becomes same. Now rest of the atoms we have to balance. 2 2s are 4. Here 1 chromium. So what we have to do? We can multiply this is by 4 times. So 4K2, this becomes 4. So 4 2s are 8 chromium. 4 chromium plus 4 chromium 8. Oxygen 4 7s are 28. 4 4s are 16. 16 plus 6 22. 2 3s are 6 28. That's all the action of heat on the potassium dichromate. The next reaction is very important set of reactions. From this we can expect questions. See, potassium dichromate being existing in its higher oxidation state of +6, that it can be used as oxidizing agent, because the +6 oxidation state, the last class we discussed about that Frost diagram where +6 oxidation state whose del G naught value is found to be positive, but the compound with the positive del G naught is highly unstable. That's why it has to decrease. That means it has to achieve their stable state. Because of that only dichromate is behaving as an oxidizing agent where it reduces to its stable oxidation state of +3. So let us find this behaving as an oxidizing agent. So when this oxidizing agent is taken in an acid medium where the chromium it requires, how many electron we have to identify. So Cr2O7 it is in +6 state, but it is reduced to 3+. How many chromium? 2 times. So I can multiply this is by 2. So how many electron it requires? For 1 chromium 3 electron require, 2 chromium 6 electron require. So it receives 6 electron. So the all oxygen atoms are being formed as water. So I can multiply this is by 7. 7 2s are 14 hydrogen. So H plus is multiplied by 14. So during this reduction reaction, the E naught of this equation is found to be 1.33 volt. So higher positive value, the reduction potential with the higher positive values usually behaving as oxidizing agent. So this is what one of the half reaction. So being an oxidizing agent that can oxidize the other compound. Let us find one by one. So to understand the reaction, we need to know only the two things. The transfer of electron must be same between an oxidant and an reductant. So let us find one by one. Oxidation of ferrous to ferric. So dichromate ion with the ferrous ion, it with in presence of acid medium only we are going to take. So in all acid medium we have to find that H plus alone. And the first half reaction is the standard half reaction. That means chromium, whatever be the compound being oxidized, that has to provide 6 electron. That is the constant one. So Fe2 plus to Fe3 plus, that can give only 1 electron. So we can multiply this Fe2 Fe3 plus by 6 times, because chromium requires 6 electron. Now chromium Cr2O7, the same balancing can take 2 Cr3 plus 7 H2O. Now you have to balance the H plus, so it is 14 H plus, that's all. So when you remember the first half reaction, then the rest of the reduction reaction, that means the redox reactions will be so easy to balance the one. So here once again we have to balance the charges. In the previous cases also you can find 2 minus 14 plus and 6 minus. 14 minus 8, that is equal to 6. 2 3s are 6 plus. Here 2 minus 14 plus with the 6 2s are 12 plus. Totally 14 plus 12, 26 plus. So I have to get 26 minus 2, 24. Here 2 3s are 6, 6 3s are 18, 18 plus 6, 24. So charges also be balanced. The next one, oxidation of iodide to iodine. So the iodide, any iodide salt we can have potassium iodide or sodium iodide, where the iodides are converted into iodine. So here also the oxidation number decreased because iodine approaches zero oxidation state. So one iodide can give 1 electron, but how many iodine I have in a molecule? 2. So I can write here loss of 1 electron with the 2 iodine atom, that makes it is equal to 2 electron. But chromate, how many electron it requires? 6 electron. All the 6 electron must be given by the iodide. So what we can do? The entire equation can be multiplied by 3 times. So this becomes 3 times, 3 2s are 6, this becomes 6. That's all. I balanced the iodide. The rest just from this equation I can write this is 14H plus, this is 2Cr3 plus, this is 7 molecules of water. Charges also be balanced. 6 minus 2 minus, totally 8 minus, 14 plus 14 minus 8, 6, 2 3s are 6. The next one, oxidation of sulfide to sulfur. Here sulfide it is in -2 oxidation state, iodide it is in -1 oxidation state. So in this sulfide is oxidized to sulfur, therefore there is a loss of 2 electron, loss of 2 electron, but chromium it requires 6 electron. So what we should do? We have to multiply this 2 by 3 times, therefore sulfur multiplied by 3, so this sulfur is also multiplied by 3. The rest we can balance. Here it is 14H plus, here it is 2Cr3 plus, here it is 7H2O. Charges will also be balanced just like the previous one. 6 minus 2, 8, minus 6 minus 2, 8, 14 minus 8, 6, so 2 3s are 6. Oxidation of sulfur dioxide to sulfate. So sulfur dioxide, we should find what is the oxidation state of sulfur. Oxygen -2, 2 into -2 -4, so sulfur equal to +4, so this is +4 state. Now what about oxidation state of sulfate? Oxygen 4 times, 4 into -2 -8, -8 that side +8, here we have to equate with the charge. So what we will do? SO4 2 minus, we can write x -8 -2 or x equal to +6. Therefore oxidation state of sulfur in sulfate is +6. So how many electron being lost by 1 sulfur? 2 electron. So there is loss of 2 electron. How many electron chromium requires actually? 6 electron. So once again multiply, this is by 3 times. Therefore sulfate also by 3 times. Correspondingly sulfur dioxide is also by 3 times. Now balance the equation because we need to balance the number of oxygen atom. Here 7, 3 2s are 6, 7 plus 6, 13 oxygen atom. Here 3 4s are 12, 12 plus 1, 13. So how many H plus ion require? Only 2. So this is 2H plus. So now balance the charges. 2 minus 2 plus equal to 0. 3 plus 3 2s are 6 minus, sorry, this is 2 chromium, it is multiplied by 2 times, 2 3s are 6 plus, 3 2s are 6 minus, 6 plus 6 minus, balanced. The next one, oxidation of stannous to stannic. SN2 plus is stannous form, SN4 plus is stannic form. In this case SN2 plus changes to SN4 plus, so you may find there is loss of 2 electron. Okay, last 2 electron but require 6 multiplied by 3. So this is 3SN4, this is 3SN2 plus. The rest we can balance just like before. So this is 2Cr3 plus, 7H2O, 14H plus. That's all the balancing of the chemical equations. Very simple reaction. So to remember the equations or to remember the balancing of chemical equation, need to have lot of practices. The next one, chromyl chloride test. Actually, this test is being performed for identifying the chloride radical. Actually, this is what taken for qualitative analysis of salt. So, in this, when we have the chloride salt, this chromyl chloride test is to be considered as one of the confirmatory test for the presence of chloride radical. So, chromyl chloride, that is nothing but a red orange vapor. It is formed when we treat the chloride salt with potassium dichromate in presence of an acid medium. So, the sodium chloride is taken, any chloride salt you can have. When this chloride salt is treated with the potassium dichromate in an acid medium, say sulfuric acid, the vapors of red orange chromyl chloride is formed. And along with this, potassium hydrogen sulfate, sodium hydrogen sulfate also formed in addition to that water. This reaction, a simple reaction in which none of the element undergoes oxidation or reduction, because chromium here plus 6, here also plus 6. How it is plus 6? This is 2, for chlorine minus 1. So, 2 into minus 1 minus 2. Oxygen minus 2. 2 into minus 2 minus 4. Minus 4 minus 2, that is equal to minus 6, and hence its counter charge will be plus 6. So, as there is no change in the oxidation number of any of the element, you can simply balance the reactions by counting. So, 2 chromium, this is multiplied by 2 times. How many chlorine we have? 4. So, sodium chloride is multiplied by 4. How many sodium I have? 4. So, NaHSO4 is multiplied by 4. And potassium dichromate, I have 2 potassium. This is 2 KHSO4. Now, count the number of sulfate. 2 SO4, 4 SO4, totally 6 SO4. So, here I am getting 6 H2SO4. Count the number of hydrogen, 12 hydrogen. Here 4 hydrogen, here 2 hydrogen, 6 over. I need 3 more hydrogen. So, 3 H2O. Sorry, out of 12 hydrogen, 6 over, I need 6 more hydrogen, so 3 H2O. Now, oxygen, it is simply balanced, 7 oxygen, 2 2s are 4 oxygen, 4 plus 3, 7 oxygen. Sulfate, no need to consider, because we counted sulfate as the radical. We didn't count sulfur or oxygen. So, now this red orange vapor, when it is passed through sodium hydroxide solution, we will get a yellow solution of sodium chromate along with the sodium chloride and water. So, the red orange vapor, when it is passed through sodium hydroxide solution, then chromyl chloride is converted into sodium chromate. Now, we have to balance the equation. Here also none of the element has changed their oxidation state. So, this is plus 6, this is also plus 6. So, balancing by counting only. Here 2 chlorine I have, so NaCl 2 times, and sodium 4 times present, NaOH 4 times, oxygen 4 plus 2 6 times present, 4, so water will be 2 times, and hydrogen we can have 4 hydrogen, this is 2 2s are 4 hydrogen. Now, this sodium chromate, when it is treated with lead acetate, we will get the precipitate, yellow precipitate of lead chromate. The previous case we got yellow solution. This is present in aqueous form. When it is treated with the lead acetate, we will get the yellow precipitate of lead chromate and sodium acetate. Once again balance. This is also not at all redox reaction. 2 acetate groups, so 2 times CH3COO Na, and lead 1 time, this is also lead 1 time. That's all the chromyl chloride test. In this case, if at all you have Viva, you know, they may ask the oxidation state of the element, or whether the reaction follows redox reactions or not, or they can ask what is the formula for chromyl chloride. That is very important question and most important. So, in this, then why the yellow precipitate is formed? It is because of the formation of lead chromate. So, such a way you have to analyze the equations to answer for your Viva. Then what are the uses of potassium dichromate? Dichromate, it finds its applications in most of the industrial cases of manufacturing of dyeing as well as in printing. Then also it is used as an oxidizing agent. Then it is used in the tanning of leather. Nothing but that animal hides has to be preserved. That is called the tanning process, in which also potassium dichromate is used. Then it is also used as an analytical reagent. See, here it is used as an analytical reagent to identify the chloride ion. Similarly, the potassium dichromate can be used to estimate the amount of iron or the iodine present in a given compound. That's all the preparation and properties of potassium dichromate. Okay students, let us close our today's session. Today we discussed about the potassium dichromate whose preparation and properties alone. Let us continue the same chapter in our next session also. Until then, bye bye.